Good morning, everyone. My name is Guizhen from Deakin University. Today, I will present our work entitled Poisoning-Based Link Inference Attack Against Federal Graph Neural Network. In our work, we consider a scenario that there is a healthcare system under Federated architecture. In a global graph, each hospital trains a local GNN model that contributes to the federated learning process coordinated by the Medical Administration Center. So in this case, an attack has compromised hospital K and control its local training processing. The attack wants to know patient private information, such as if a patient U is also the patient of the other hospitals, or if a patient B has a relationship with U. The attack ingests the perturbation into U, and this perturbation propagates to U's neighborhoods via both intra-client and cross-client edges. If there is a link between U and V, like the family link or the same patient appearing in the multiple hospitals, this perturbation on U induce the observable changes in this output. Otherwise, no shift occurs. So we can see that while Federated allows hospital or institution to train a model on distributed graph data without sharing the raw patient records, they introduce a significant privacy gap. The core of the problem is the message parsing. So by exchanging information over cross-client and intra-client edges, the rational information is encoded into the null representation shared during the training, and this allows the attack to perform link inference attack to uncover sensitive relationships like the digital relations or the social links, even without accessing to the raw data. So based on the considered scenario, we propose our threat model. We consider an attack who is a malicious client participating in FedGN protocol. We evaluate two knowledge settings, black box setting. The attack only sees the global model outputs, and white box setting. The attack has access to global parameters, but cannot access to the other client's data and the local updates, and can manipulate its own local training. The attack capabilities include generating local nodes and conducting local annotation to steal the global model. As a participating client in FedGN, the attack has the same view of their protocol as the honest clients. The attack goal is to determine if a link exists between U and V. Based on the threat model, we propose our link inference methodology, which is based on the intuition that poisoning can reveal structural secrets. The attack follows four main steps. First, the attack injects poison into the candidate node U within the local subgraph. Second, the message parsing mechanism propagates this poisoning information through both intra-client and cross-client edges. Then the attack monitors the output distribution of the target node V. If V is a linked neighborhood, if you experience an output shifts in its probability distribution. Finally, by comparing this shift against a threshold, the attack can infer the link existence. In our proposed methodology, we have two poisoning link inference strategies. Our first strategy is label flipping link inference attack. It operates in a black setting. The intuition is straightforward. The attack lists the label of node U. For example, change the paper's categories from genetic algorithm to reinforcement learning. This ingests a malicious information that propagates through the structured topology during the training. So if U is connected to V, this poisoning information causes a change in V's output distribution. By comparing these changes against a threshold, the text can infer the link existence between U and V. For the whiteboard setting, we propose our second strategies, gradient ascent link inference attack, which the attack performs gradient ascent on the loss of no U. This specifically reverses the loss objective to amplify those use representation shifts. By comparing this shift against a threshold, the attack also can infer the link existence. We conducted an extensive evaluation using 5 benchmark datasets, including the homogeneous graph dataset and heterogeneous graph dataset. We also testing our attack across 3 major GN architectures and assess them against several aggregators, as well as the baseline like the STA and LTA. Our experience utilized a federated setting with 5 clients, including 1 malicious client. We use an overlapping rate of 0.3 and launch the attack at 215 Aprils, which is near the point of model convergence, providing a stable baseline for measuring shifts. Here is some results. Table 2 shows that 2 proposed strategies consistently outperform existing baseline, especially for the gradient ascent link inference attack. It's more powerful. It often achieves over 90% precision across various datasets and aggregators. Furthermore, Figure 5 illustrates the impact on the model utility when the attack is launched. Training accuracy drops significantly for undefended models, while robust defenses like XL detector, it mitigates the drop, but it cannot completely prevent the link inference leakage, which highlights the challenge of countering this structural threat. We also conduct amplification studies on the impact of overlapping rate, the number of attacks, and the attack launch timing. If you are interested, please refer to our work paper for more details. In conclusion, we have introduced a novel poisoning-based link inference attack framework. Our extensive experience demonstrates that property perturbation can effectively reveal hidden structural links in FedGN. And also the key finding is that the gradient ascent link inference attack consistently achieves the better performance. Thank you.